Hello dear all. Today we are going to talk about free convection. This will be our first video, and then boiling. This will be the next video, and then condensation. Okay. First, the free convection, or it is also called natural convection. Okay, they are the same words, free or natural. So free convection happens. These are the applications of the free convection where we see the free convection. So if we have any hot surface without external means, okay, so this one can be fan, or we can have the pump. Okay, so if you don't use any external means, it is free convection. For example, if you look at here, so here you have the cup of water. So this part is hot, okay, and this part is cold. Okay, if it is hot, it means that it has low density. If it is cold, it means it has high density. Okay. And this one has a low density, therefore it is light. This one is high density, therefore it is heavy. Okay. So since it is light, it will rise. And since the fluid rises, you will have heat transfer. Okay. So you shouldn't mix the fluid flow with the heat flow. Here, these are the fluid flow. Okay. But as the fluid rises, it carries heat. Therefore, this is free convection. But this one is forced convection because you are using fan or you blow on the water. Therefore, these are forced convection. But this is not purely forced or purely free. This is mixed convection actually, mixed CV. Because in that direction you have forced CV, okay, and in that direction you have free CV. It is not pure, but here it is purely free convection. Purely free convection. Another application of the free convection is a thermohaline, okay, and atmospheric circulations. These are two atmospheric applications of the free convection. So you can search for these two in the web, okay, look for it. But in the short terms, thermohaline regulates, this one regulates, okay, T in oceans, okay, and this one regulates T on Earth. This one regulates T on oceans because you see on the poles we have the cold weather, and in the equator or the tropics we have the hot weather, and this one regulates the temperature in the oceans, and this one regulates the temperature on Earth. Because otherwise, if you don't have thermohaline or atmospheric circulation, one part of the Earth will be very cold and on the other part of the Earth will be very hot. Okay, but these two regulates the temperature difference. Another application is the thermosiphoning. Thermosiphoning is mostly used in solar collectors. I can show you thermosiphoning here. You can see here, this one is the thermosiphoning. Here you have the hot fluid. This hot fluid rises and replaced with cold fluid, and cold fluid falls and rises. Okay, this is called thermosiphoning because here you have the siphoning process. Okay, siphoning. If you know siphoning, so you have a tube here, okay, and the fluid rises from that tube, and here you have the vessel, okay, and the fluid rises in that tube. Okay, this is called siphoning. But here you have fluid siphoning. But in this case, you have the thermosiphoning, or you can say the temperature siphoning or heat siphoning, because you are siphoning heat from one place to another. Okay? And we have the clouds. These are the result of the natural convection because due to density difference, the water vapor rises and then it condenses, becomes clouds. Convection currents of Earth and the chimney effect. This is the, again, I can show you chimney effect. Okay, this is also free convection, you can see here, and here you have the low density, and here you have the high density, and the low density fluid rises and the high density fluid sinks. Okay, and this recirculation is chimney effect. Okay, or natural ventilation. Okay, so here you don't use any ventilation, but the natural, it happens by itself. The last part is the winds. Okay, these are also the natural convection. This one is due to density difference again, and it creates pressure difference, and then you have the winds. Okay, but for atmospheric parts, thermohaline, atmospheric circulations, winds, okay, these are very complex phenomena. Okay, this is not as simple as we are talking about, but anyway, these are the applications of the natural convection. And for the natural or free convection, we have this one is difficult. Again, we have said that any convection problem is difficult, complex. Okay, you will see that it is more complex than forced convection. And we have applications or solutions, we can say correlations. You can see the simple geometries, plates. It can be vertical plate, something like this one. It can be inclined plate, something like this one, and it can be horizontal plate. Okay, these are all hot. Okay, hot. It can be cold also. Okay, it is also possible that it can be cold. Okay, therefore, let's write this part. It is possible that they are also cold. And you have the vertical cylinders. This one is the vertical cylinder. Okay. You can have the horizontal cylinder, natural convection, and you have the enclosures. Something like this one, 2 plates. This one is horizontal, so first horizontal enclosure and then vertical one. So horizontal enclosure, you will have something like this one, 2 horizontal plates. Okay, and the inclined, you will have something like this one, and the vertical enclosures, you will have something like this one. Okay, or you can have the concentric cylinders. You have cylinder, you have another cylinder here, but it is in 2D. Okay, or concentric spheres, you have 2 spheres, and we have solutions for the spheres. Okay, and you have the solutions. You have the solutions for the finite surfaces and the PCBs, which is the printed circuit board. Okay, we'll look for some of it. Okay, so we will look for some of correlations, because you cannot do all of it. Okay? But at the end, you should know that this is correlation, experimental results. Some of these plates, for example, can be analytical, simple solutions, but if it becomes complex, like cylinder spheres or PCBs, it is exactly a correlation. Okay, for example, this one is correlation, experiments. Okay, all experiments. And here we have some recapitulation from fluid mechanics. If you remember it, we have the coefficient of compressibility, isothermal compressibility, and the volume expansivity, and the temperature coefficient of resistance. Okay, but we will here talk about this one, volume expansion coefficient, beta. What it says that it shows how volume changes per unit temperature difference. Okay, so if you have 10 degrees Celsius, how volume changes with respect to initial volume. Okay, that is the definition of the volume expansivity, but pressure is constant. Here you have isothermal compressibility. It shows how volume changes with respect to pressure change. Here you have temperature change, here you have pressure change. And the inverse of it is called kappa. It is modulus of elasticity or coefficient of compressibility. And the last one is the temperature coefficient of resistance, and it shows how resistance changes with temperature change. Okay. And we will use this one in free CV. We will use this one. Okay. Let's talk about this one a bit more. And you can see here we have the Rayleigh. Okay, in this Rayleigh you can see there is a small gap here. So if I put it closer, you can see this small gap over here. So we have a small gap here. Okay, and this small gap is due to volume expansivity, which is called beta. We have talked about this one. Beta. We have said that beta is delta V by volume initial by delta T. In this case, it is not 3D, it is 1D. Therefore, we can approximate this one as delta L by L divided by delta T. How length changes per initial length. This one is initial. Here you can see, if it is hot, this one will expand. As it expands, if there is no place, if there is no gap here, so you will have a curve, something like this one. Okay? And similarly here you will have curve, something like this one. Okay? Therefore, we are leaving some gap. So therefore, to prevent any expansion of the material here. And we have another example here. This one is the thermometer. So you have the thermometer here, and you can see here we have the T1 and with some initial volume, and we have T2. You can see the volume has increased. Okay, so again, if you apply it, delta V by initial volume, apply temperature difference, which is T2 minus T1, and this one is the beta. This is the definition of the beta, and you will see that we will use this one in free CV. In free CV relations, we have the beta. And if it is ideal gas, you can find the beta value very easily, because for ideal gas we know that P nu is RT, or you can write PV is MRT. Okay. And for this one, if you go back to formula, you should take the derivative of volume with respect to temperature. Okay, derivative of volume with respect to temperature. If you do that, and the volume is equal to mR by P into T. And if you take derivative, but you should take at constant P. See here, P constant. If the P is constant, then derivative of volume with respect to temperature will be mR by P. Okay, and then what you will do, you will divide by initial volume, and initial volume is this one. Okay, let's do that. So you can see here 1 by the volume in the derivative of it. Okay, and derivative of it is mR by P divided by initial volume. You will get, let's do that, mR by P divided by mRT by P, and you will have 1 by T. So therefore, for ideal gases, beta is 1 by T, but this T in Kelvin, it should be in Kelvin scale. So now we'll look for the boundary layers for the free convection, and as always we will have the boundary layer that develops on the, this one is hot, or it can be cold. In this case it is hot. Okay, so you have the growing boundary layer, and at some place you have the maximum velocity. This one is maximum velocity, and here you have the two minimum velocities. Okay, but the difference between this one and the forced convection is that in this part you have the quiescent air fluid, or you can say. Okay, and this quiescent fluid has T infinity, but U infinity is 0. Okay, U infinity is 0 here. Therefore, at some point you will get them. Here you have the 0 velocity, and here you have the 0 velocity because this one is due to quiescent fluid. Okay, or fluid, you can say, is that doesn't move, and you have 0 here, and you have 0 here, and you will get some maximum value in between. The velocity increases, and you have the maximum value, and then we drop the 0 value again. And if you look for the temperature, you will have the Ts here. This one is the Ts value. As you move along across the surface, you will have T infinity here. Okay, and then again here you have the U infinity is equal to 0. And since you have the boundary layer, and then you will have the H value, and we have talked about H value in our previous lectures, that is H is K by delta T, and this one is delta T, thermal boundary layer thickness. Okay, and here, no, this part is delta T should be here, because this one is the velocity boundary layer. You should have the delta T here. Okay, you have the boundary layer thickness and the K value, which is conductivity. So if you see, if the K value delta T increases, you will have the less H value. You have the maximum H value here, and you have the minimum H value here. Okay, this is the concept of the natural convection heat transfer coefficient. And the main difference between this one and the flat plate is that, if you remember it, on flat plate, on external forced convection, so this one is external forced CV, you have again the boundary layer growing, but here you have the U in is 0, and here you have the U infinity. Velocity increases from 0 to infinity, but here you have the 0, and you have the 0, and velocity gets the maximum and drops it. It's very similar to, you have two confined plates, and this one gets the, this boundary layer grows, this boundary layer grows. Here you have the maximum velocity, okay, and in between you will have the minimum. Okay? You will have something like this one. Okay? But here you don't have the solid boundary. Here you have the air, but here you have the solid boundaries. But the profile is same, okay, and the solutions are same. Okay, solutions for the boundary layer and this one are the same. And in forced convection problems, we can neglect the radiation. Okay? It is very small with respect to forced convection value, but in natural convection it becomes important. Okay? If the medium is gas, especially because natural convection has H value small. And we have here the pure conduction and the natural convection. So when it is the pure conduction, when it is the natural convection, here you have T1 and here you have the T2. If it is pure conduction, air is silent, okay, it doesn't move, or we can say the quiescent, it doesn't move. Okay. If it doesn't move, then you have the advection 0. Okay. If advection is 0, then it is pure conduction. If I take some thickness here, L, okay, then heat conduction in that direction, that will be Q dot. Okay. That Q dot will be equal to K into T2 minus T1, okay, divided by the thickness L times the area. Okay, here you have the area that heat is transferred. Okay, this area, three-dimensional, and here you will have the area. But if you go back to here, you have the advection here. So advection here is not equal to 0. Since advection is not equal to 0, you have the convection. And I can write the convection problem again in the same manner. You have T1, and here you have the T2. But instead of K conduction equation, I will write the convection equation. Here you have again Q dot, and that will be equal to H, again area, and T2 minus T1. Okay, and they have the same area. Okay, they have the same area. But the problem here is that you have the convection here and you have the conduction here. So I know the Nusselt number is equal to H L by K. Okay, therefore instead of value of H, I can write Nusselt number K by L. That one is exactly equal to H. If I replace this value back to here, I will have Q dot is equal to H instead of H, Nusselt number K by L, and you will have Nusselt number into K into area into delta T divided by L. And you can see this equation and that equation are exactly similar. Okay, if they are very similar to each other, this can be treated as conduction. If it is treated as conduction, then Nusselt number into K will be the conduction coefficient. Okay, this one is K, and this K is called K effective. Okay. If Nusselt number is 1, okay, K effective is exactly the same as K. If they are equal to each other, then it means that this conduction, there is no convection here, this is purely conduction. If Nusselt number is greater than 1, you will have the advection effects or recirculation effects here, and therefore you cannot treat as pure conduction problem. Now we will go back to second case of the natural convection. So here you have hot plate and here you have the cold plate, and since this part is hot and this part is cold, here you have the T high. T high means low density. Here you have the T low. T low means high density. Okay. Since high density fluid is heavy and this one is light, okay, heavy fluid cannot rise. Since it cannot rise, then you will have the stable temperature gradient and therefore stagnant fluid. In this case, you will have the opposite of it, and then you will have a non-stagnant fluid. You will have something like this one, circulations inside the tubes, because hot one rises, becomes cold, denser, okay, and then falls. Again, you have this circulation. And the main important non-dimensional number in natural convection is the Grashof number. Okay, Grashof number shows the ratio of the buoyancy force over viscous force. Okay, here you will have the G, the beta that we have talked about. The beta is the expansivity, and Ts is the surface temperature. Here you have the Ts, and T infinity is the surrounding temperature. Here you have the T infinity, and the L characteristic is the characteristic length. Okay, it can be the height of the plate if it is in this direction. It can be width of the plate. Okay, it depends on the direction of the flow and the geometry. And the mu is the kinematic viscosity. Okay, this is called the Grashof number, and the Grashof number shows the ratio of the buoyancy force over viscous force. So if you look at here, this fluid rises, okay, because you have the hot fluid that rises. Since this fluid rises, it has buoyant force, because it has low density, and opposite to that force you will have the viscous forces or frictional forces. Okay. If buoyancy force is more, then fluid will rise, and then you will have the Grashof number greater than 1. Okay. It is very similar to Reynolds number. Okay. In Reynolds number, we are comparing inertial forces, or MA, acceleration, over viscous forces. Here we are comparing buoyancy forces over viscous forces, but they are very similar. This one is used for forced CV, and this one is used for free CV. And another non-dimensional number, which is the Rayleigh number. So in natural convection, heat transfer coefficient is function of Grashof number and the Prandtl number. Okay, and to make the things easier, what we are doing is that Grashof number multiplied with the Prandtl number is Rayleigh number. Okay, therefore H becomes function of the Rayleigh number alone. Okay, makes easy. And here you can see we have introduced Rayleigh number, and the Rayleigh number determines the value of the H. And since we have said that Grashof number plays the similar role as the Reynolds number, and for the Reynolds number we know that if it is less than 23 hundredths, it is laminar, or if it is less than 5, 10 to the 5, this one is internal, this one is external, and then you have again the laminar flow. But similarly for Grashof number, you can see after some value of the Grashof number, it is called critical Grashof number, similar to critical Reynolds number. For vertical plate, it is around 10 to the power of 9. Okay, so it means that after the value of 10 to the 9, you will have here turbulent flow. Turbulent means that you have eddies, mixing, okay, random chaos, and then, but this part is the laminar. You can see the straight lines here. This part is the laminar. Okay, and we have the natural convection correlations. I have selected one for here for the range of 10 to the power of 4 and the Rayleigh number to the 9, and you have the Nusselt number correlation given as this one. As we have said, we are talking about the Rayleigh number because it makes things easier. Okay, and this is the correlation for the Nusselt number, and from this Nusselt number, as we have talked about in external convection, we are finding the H, because Nusselt number is K by L. This one gives you the H bar, average H. This one is for vertical plate. For the horizontal plate, so if you compare the H value, this one has H vertical, this one is H inclined, not horizontal, inclined. If you compare the H values for this one and for that one, for the vertical plate, H value, H vertical, is less than H inclined. This one is both hot. Inclined but upper part, because if you look at here, so here you have the boundary layer growing something like this one. Okay, and the buoyancy is in that direction, buoyant force, and viscous force in that direction. But here you have boundary layer growing something like this one, and in that case you will have X component and the Y component of the buoyancy forces. Okay, buoyant forces. And since you have the Y component of the buoyant forces, it means that this boundary layer, if it is very similar, if buoyant Y direction is very strong, okay, if it is very strong, it will break this boundary layer, and you will have something like this one. Okay, and this one is called the plume. This one will break the boundary layer. So as it breaks the boundary layer, okay, it will break boundary layer. Okay, as it will break the boundary layer, you will have heat flow in that direction. Okay, and so it means that heat flow is not confined to one space. As it is not confined to one space, you will have better heat transfer. Okay, because boundary layer is resistance. If you have flow in that direction, you have better heat flow, and therefore you have better H, because boundary layer is broken. But in this part, the lower part, you will have lower H, because if you go back to here you don't have any way to break the boundary layer, because viscous, if buoyant force have Y direction in that way, but it cannot penetrate the wall here. Therefore, in Y direction you don't have any separation of the boundary layer. Therefore, in upper part it is more, but in lower part, H inclined, it is less. Okay, it is less. And the similar things happens for the cold plate. For the cold plate, this one is cold. Okay, this one has, let's say, Ts, and here you have the T infinity, and the T infinity is greater than Ts. And here you will have the opposite manner. So the opposite manner will be, this part is the heavy part and this part is the light part. So this one is light and this part is the heavy air. Okay. And here you again the heavy air, and here you have the light air. Okay. Okay, you will have the boundary layer, something like this one. Okay, and again you have the point force, and in that direction you have the viscous force. Okay. But in lower part of the plate you will have again the plumes, because this boundary layer will break again, because again you have F buoyant y direction. Okay, it is more. As it is more, it will, if it is strong, it will break the boundary layer, and you will have the opposite case in the cold plate. Okay, so for the horizontal plate, this one is horizontal, okay, but again hot. So in this case you will have again the similar manner. So again you have the plumes here. Okay. And the last case will be the cylinder. If you have the cylinder, you will have the boundary layer, something like this one, cross until this part is wrong. Let me draw it again. You will have the growing boundary layer. You will have the growing boundary layer. Okay. And similarly on the other part you will have growing boundary layer. As you can see, here you have more thickness and you have more thickness. As you move along it, you will have more thickness. Okay, so if you have the more thickness of the boundary layer, so this one is delta T increases. Okay, delta T increases as you move in theta direction. As delta T increases, you will have the drop in Nusselt number, because Nusselt number is HL by K and H value is K by delta T. As H value, delta T increases, H drops, Nusselt number drops, and you will have sharp drop in Nusselt number till this part, because you have here, you can see the value of the delta T, it increases sharply. Okay. As for all of these cases, this one and the other one and here you have the correlations. Okay, for all of these you have the correlations, and now we have the here enclosure. This one is the enclosure. Okay, but this one is vertical. This is similar to vertical plates, so you can go back to here, vertical plate, but here you have two vertical plates in face to face. Okay, with these two vertical plates you will have one boundary layer that grows from one vertical plate, you have another boundary layer that grows with the other vertical plate, and they meet up at some place. Okay, if they don't meet, then you will use two vertical plate correlations, but if they meet, you will have the enclosure. Okay, if you have an enclosure, you have the correlations. So we have the H by L. Okay, so this one is also called the aspect ratio. Okay, for this aspect ratio we have different correlations. If it is between 1 and 2, you have this one, and for the difference of the Rayleigh number, and if it is 2 and 10, you have this correlation. 10, 40 between Prandtl number of 10 to the power of 4 and 1, you have this correlation. Okay, different correlations for a different Rayleigh number range and the aspect ratio range, and all fluid properties should be calculated at Ts1 plus Ts2 by 2. Okay, we have the correlations for the fins. Okay, in this case we assume that the Ts is constant. Okay, so this one has constant Ts, this one has constant Ts, constant surface temperature. Okay, and the Rayleigh number is based on S. It will be this one. Based on L you will have the Rayleigh number, and then for the Nusselt number based on S you will have the correlation here, and also we have the optimum thickness. Okay, optimum distance between two plates, because if this S is very small, if it is very small, yeah, then you will have H value will drop. Why it drops? Because you don't have any good contact for the air. So because air rises in between and air rises in between, but if it is very close to each other, it means that you don't have any gap for the travel of the air, then you will have the suffocation. Okay, we call it suffocation. Therefore the distance should be in an optimum value. Okay, for optimum thickness you will use this relation. Okay, and then Nusselt number is 1.3 for when S is optimum. Okay. These are the correlations, experimental values, and we can find the heat transfer by this relation, where N is the number of the fins. We divide this W by S by T, this distance, okay, you will get the number of fins, how many fins you have. Again, all properties as Ts plus T infinity by 2. And you have the PCB correlations. In this case, the heat flux is constant. You have the constant heat flux, you have the Rayleigh number, you have the Nusselt number, and again you have the optimal thickness, optimal distance between these two plates. Okay, all properties at T plus T infinity by 2. And the last part will be the Richardson number, which is Grashof number by Reynolds number square. Okay, and it shows the free versus forced. Okay, which one is important? If Richardson number is much greater than 1, it means that Grashof number is much smaller than Reynolds number square. Then it means that forced CV is dominant. Okay, if Richardson number is much greater than 1, it means that Grashof is more than Reynolds number, and it means that free CV is dominant. Okay, but if the Richardson number is approximately 1, you will have the mixed convection. Mixed means free and the forced, all of them are important. In that case, the simple approach to find the H value is to take the maximum of the HFC or H natural convection. Okay, you can take this one or you can take that one. But the more sophisticated approach, we will take H bar value as the maximum of the HFC, okay, to the power of m, and that plus minus the minimum of the HFC to the power of m, 1 by m. So here m value is the 3 value, okay, and the plus means that this one plus. Positive. Positive means that forced CV and the free CV are in the same direction. Okay, so they are helping each other. Okay, they are augmenting each other. But if they are, so we call it assisting flow. Okay, assisting flow. But if they are in opposite direction, free CV in that direction, forced CV in that direction, you will use the minus sign. Okay. So you can see here we have the assisting flow. This is the direction of the forced CV. This is the direction of the buoyant flow, which is the natural CV or free CV. This is assisting. Okay, and here you have the fan. But in that case, you have the falling fluid. You can see this one falls. As this one falls, you have opposing flow because they are in opposite directions, and therefore you will have the minus sign in this equation. And the last case is the transverse flow. Transverse flow, this one in that direction and normal to that direction. Okay, this one is normal, forced, normal to free. Okay, in this way they are also helping each other because this one is opposite direction to that one. They are helping each other. Again, it is positive here. Okay. And we will have examples here. Okay, so examples for natural convection, we will solve them, and then we will talk about the boiling and the condensation.